Are we still waiting for?
No, we can start, like, I think now.
Okay, perfect. Yes.
Um,
I'll just start my stopwatch as well. Thank you for inviting me.
for joining us.
No worries. So this is the work I've been doing as part of my PhD. The paper has gone out to reviewers hopefully soon. Um, I've started continuing on this work now, but the main idea of this talk is that we have developed this new SED fitting method, which we call simultaneous SED fitting, and for the first time we apply this method to constrain AGN torus parameters at cosmic noon. I'll break down what all those things mean. But please feel free to interrupt me if you have any questions, or if you feel I'm going too fast or too slow. Please interrupt me um, in the middle. Yes. So why do we before going into AGN torus, why do we even care about AGN? One might ask. You probably won't ask, but someone might ask, why do we even care about AGN? Well, oh, my slides. Okay. Well, AGN, we might not care about AGN onto themselves, but we care about galaxies. And AGN and galaxies are known to co-evolve. For example, in this plot, sorry, I'll just minimize the. Um, so, for example, in this plot, we see this is a well-known M sigma relationship between the central supermassive black hole in galaxies and the velocity dispersion, or even you can even take it as a proxy for galaxy mass. So there is a tight correlation between the mass of the central black hole and the galaxy stellar mass. What else? We know galaxy AGN are some of the most energetic phenomena in the universe. So they accrete material from the galaxy. So they deplete galaxy of gas, dust, which could be used for star formation or other stuff that galaxies do. They also inject a lot of energy back into the host galaxies. So um, they can quench star formation. They can even trigger star formation in some cases. So these two things affect each other. For example, this recent work showed that if you have two populations of AGN, two populations of galaxies which are analogous to each other, but one has an AGN and one doesn't have an AGN, then you see different star formation, different metallicity in the galaxy properties. Um, so yeah, galaxies affect black holes and black holes affect galaxies. For those who care about X-ray astronomy, AGN form the biggest component of the cosmic X-ray background. So they are essentially what you would like to study if you want to study cosmic X-ray background. And those people who don't care about galaxies at all, those who do cosmology, well, AGN are important to match your simulated galaxy properties to what we observe in the real universe. So, for example, in this plot, if you don't have any AGN feedback, you end up producing this green line in your simulation, which produces so many massive galaxies as compared to what we actually observe in the universe, which is this pink line. So you need feedback from AGN to sort of stop this growth of galaxies. So that's why we care about AGN. So because of all these nice properties, people had started studying AGN. They started studying AGN in optical wavelengths, but they quickly realized that AGN emission is actually quite varied and quite broadband. So you see, there is stuff happening in X-ray, there is stuff happening in radio, mid infrared, everywhere. So um, this puzzled scientists for quite some time as to how do you produce such a broadband emission from a single black hole which is accreting some matter. And when astronomers are puzzled, what do astronomers like to do? They like to classify things. So they classified AGN into different classes based on their spectral properties, based on their luminosity, based on whether they see radio emission or not, and things like that. The second second thing astronomers like to do is unify all these different classes after classifying. So it's kind of a feedback loop which keeps us in job. Um, so what people came up with after that was to explain this broadband emission as well as to explain all these different classes, was a unifying scheme for AGN. What is the unifying scheme? So this unifying scheme says that this is a complicated picture of a unifying scheme, but can you see my cursor on the screen? Did you say yes or no?
Yes, yes.
Oh, okay, perfect. So this is slightly complicated picture of unifying scheme, but the simplest unifying scheme was if you have a black hole, if you have an accretion disk around the black hole, and then if you put a torus or a donut around the accretion disk made of dust, then you can produce a lot of these properties. So you can produce your dust and gas um, scatters X-ray, upscatters and produces X-ray. Well, corona upscatters and produces X-rays. Your dust can get heated and it can produce infrared emission. Um, so this was the simple unification scheme. And what this unification scheme said was that you have this donut-like structure or torus structure around your accretion disk, and all the different classes of AGN and all these different properties you see in AGN is just function of your line of sight. So if you are observing the AGN edge onto the torus or face onto the torus or anything in between determines the properties of your AGN emission. That was all well and good. But people quickly started finding emission which can't be explained by this simple model. So for example, this already in 90s, people had observed these SEDs or spectra of AGN which had such a such a wide variety of this. So UV to infrared uh, emission, such a wide variety of UV to infrared emission cannot be produced with a simple dusty torus that you have. So what did people do? The natural extension, well, the natural thing to do is there is no need for this structure to be a torus or a torus of a same size. So if you relax that criteria, then you get a, a different parameter of this torus. I'll keep referring to this structure as torus, but we know it's not actually a torus. I'll refer to as torus, but in reality, it could be of any shape. It just has to be an axisymmetric structure, roughly resembling a torus. Um, so the natural extension was, well, there is no need for this torus to be of the same size. So what do? You can make this torus thin or you can make it thick, and they define this geometrical parameter as covering fraction. Mathematically, you would say that if you are sitting on the supermassive black hole and looking around in the sky, what fraction of your sky is covered by this obscuring material or the torus is defined as covering fraction. So covering fraction is quite a natural extension to orientation model. And this also gives you a natural probe for different theories of obscuration. So of obscuration or evolution of AGN in general. So this, if you notice, this is a measure of obscuration in some ways. So this is highly obscured AGN. This is less obscured AGN. So it quite naturally lends itself to be a probe of this evolutionary theories. So one of the evolutionary theories, for example, is this receding torus model, which says that if you have a more luminous AGN, then you start to erode this torus. So you start to remove material from here and go from low covering fraction to from high covering fraction to low covering fraction torus. So that is for example one of the things you can do with covering fraction, and this is just quite a well-known work which shows so this is low luminosity and high luminosity, and what you see is covering fraction in low luminosity, for example, is quite flat, and as you go to high luminosity sample, you get low excess of low covering fraction AGN. So that is a receding torus model, which so covering fraction is one of the natural predictions of receding torus model. Then you can even test some unification models, which are which are correlations between covering fraction and different spectral features, for example. Right. Around the same time, people were also looking at so this torus model. Some of the theorists might say that this is a thing that you have put in by hand. So this is kind of an ad hoc addition to explain the explain the observed SEDs or emission from AGN. So around the same time, people were also doing simulations of torus, and what they realized was how is the torus. So the questions they were asking: how is torus formed, and how is it staying stable, and things like that. So this is not one of those simulations. This is a simulation of galaxy. Uh, this is a zoom in simulation of a black hole. So you have galaxy. This is these are gases, filaments in galaxy, and then you are zooming into towards the center of the galaxy. Still not at the torus. So if you remember, torus was about 10 parsec in size. So you are still not reaching the torus scales. Now you are about the size of the torus. So what you see here is that all the stuff from the galaxy actually feeds into the torus, and it's quite a dynamic environment there. So torus itself is not a static structure, and it can change. So for example, covering fraction might change, or the optical depth might change, or things like that can change. So it's a dynamic structure. Also, it's a bridge between the galaxy and accretion disk. So stuff that gets into the accretion disk first is in torus. And then some of the recent work has also shown that the outflows that you get in AGN can also um, remove material from the torus and push it uh, outside the gravitational influence of the black hole, and even maybe outside galaxies. So that's why torus is quite a dynamical structure, both in terms of stuff falling inside and stuff going out. Um, yeah, so we already know galaxy affects what is happening in the torus, and a natural extension would be to ask if the galaxy properties are changing, then would the torus properties also change? And we know galaxy properties change. So if you go at higher redshift, for example, at what I keep calling as cosmic noon, so around time of around redshift 2, you see the star formation peaked. There were fewer heavier elements. Uh, there was more gas um, at those redshifts, so more stuff to feed the black hole potentially. And in general, galactic environment was quite different. But we don't have any theoretical predictions of how would these things translate into what you see in AGN torus, for example, or in terms of what you see in accretion onto the black hole. Um, so since there are no theoretical studies, we wanted to get some of the observational constraint to maybe hopefully um, motivate theoreticians to do some work in these areas or even start thinking about some of this work. So if whatever I said made sense to you, if I managed to convince you that there could be a cosmic evolution in torus parameters, a natural question is why have people not done this already? Why do we not know what are the torus parameters at cosmic noon, for example? Well, if you look at the galaxy at cosmic noon, this is what a galaxy looks like. You measure the how one of the ways of constraining, one of the very popular ways of constraining torus parameters is you measure flux in different filters and construct what we call spectral energy distribution, or an SED. I like to call it poor man's spectroscopy. But this is basically a broadband emission. You see, this goes from UV to far infrared. So what you do is you put an aperture on your galaxy image, construct this SED, and then you might model the SED. But as some of you might have realized, this aperture does not have only the light from AGN. This has all the physics that is going on in the galaxy. So it has stars, it has dust, all the emission from all these different components. So it's really difficult to disentangle these components in such a way that you can constrain all these different parameters independently. So what people have done tried to do is they go to really high luminosity AGN, so quasar type systems, and they have tried to constrain AGN properties in those systems, because there you can make an assumption that your AGN light dominates your galaxy light, and so on. But as you can imagine, quasars are a specific type of AGN, and if you want to study the evolution in torus, for example, then you need a sample which is comparable to what you see in the local universe. And in the local universe, we have Seyfert galaxy. We have covering fraction measurements in Seyfert galaxies, which look like this exactly. So what do we do? If I so brace for uh, uh, a great picture here now. So this is what we had. What we do now is we have JWST. If we take the same picture with JWST, these are both same 5 arc second by 5 arc second pictures, and this is such a big difference. You can see that this is actually maybe probably two different galaxies which are either merging or very close to merging. Um, so all this physics was hidden behind this fuzzy blob. And what you can do with this now is you can measure you had all the measurement from the entire galaxy already from archival data. And with JWST, what you can do is you can measure the central flux. You can construct a different SED. We refer to white SED as integrated SED, and red SED as central SED. So if you hear me say these words, it just means these two different SEDs. But as you might have noticed, this is still not good. Um, because this aperture size is about 2 kiloparsec at redshift 2. And torus is still unresolved because torus is what, 10 parsec in size, and this is orders of magnitude bigger than that. Um, so we can't really resolve the torus still. So what am I on about then? Well, we can make some simplifying assumptions. and try to do our best with what we have. Um, so these are the three assumptions that we make. First is that torus emission is a point source, which is reasonable because torus is 10 parsec and the size of this aperture is 2 kiloparsec. So point like. We assume that all of the torus emission is contained within 2 kiloparsec. So kind of an extension of the first assumption. And the third assumption is that in this aperture, we still have some galaxy light. So stars, dust, all the galaxy physics still going on. If you make these assumptions, then this is the insight that is, well, it's not even, I wouldn't even call an insight, but just a simple game that allows us to constrain the AGN parameters. What we say is, if you have these assumptions, then your AGN would be completely constrained inside this red SED, and you can probably scale your galaxy light, whatever you learn about galaxy from this white SED, by some fixed amount, and then you can model these two SEDs self-consistently. So that is the main thing that we have come up with in this work. And this is what I call simultaneous SED fitting. That you have these two SEDs and you fit both of these simultaneously with some scaling factor to account for smaller aperture. And what I've been doing for past 1.5 years is software development to get this to work. Um, So in theory, we have got an idea. We have some fuzzy idea of what we want to do. We need to construct the model obviously to fit this, and let us first construct the model, and then I might go into some details of software um, as well. Right. So we care about AGN, and we care about AGN. We start with AGN, and we need a realistic model of AGN instead of empirical templates and things like that. So we have gone with this model called Skirtor, which is two component model. So you can imagine two component model as a low density medium and high density clumps of dust are embedded in that low density medium. So just like a watermelon with like two conical cutouts. So if you remove watermelon, two cutouts from watermelon here, then you get um, this Skirtor model. And this is there are reasons of choosing this model. If people are interested, I can go into that later. Um, but basically this is quite a realistic model of torus uh, right now. These are all the free parameters that this model gives us, but two or three parameters that are important. Inclination angle, opening angle. So opening angle is related to the covering fraction. So if you measure your angle, if you have an axis of torus here, and if you measure your angle from here to the edge of the torus, that is the opening angle, and that is related to covering fraction, obviously. Then you have line of sight extinction. So you have you have obscuration from the torus, but you also have a galaxy which is obscuring your view to the AGN. So we model that as a simple screen of dust. And then so all these bold parameters are just scale parameters. So they take this SED up and down, and all these other parameters are shape parameters. Right. What else do we have? We have stars. We model stellar population as a population with decaying star formation rate. So that gives us two parameters, star formation decay rate and start of star formation time. Um, these stars are embedded inside this dust which was obscuring the AGN. So That gives us one more parameter. And these stars also heat the dust. So this galaxy dust radiates in far infrared. That gives us one more parameter, and this scale parameter, which is some of you might notice that this is quite a useful scale parameter because this is related to star formation rate. So this would allow us to calculate star formation rate from infrared. Well, infrared star formation rate later. Right. So if you have been keeping track of all the parameters, well, before that, so this is what I was calling integrated SED. It covers the entire galaxy. This is what we had as central SED. There is still some light from green and blue components, and this might give you more intuitive idea of what I mean by scaling. So if what we do in simultaneous SED fitting is that when we are fitting these points, we just scale the galaxy um, components by some amount. So if I cycle between these two slides, you would notice that AGN parameters, AGN model remains the same, the red one, and both the galaxy components are scaled by some amount. And this and we don't fit these two SEDs separately, we fit them simultaneously, and that means that we are fitting both the scales self-consistently. And this is the software development that I have been doing. So if any of you are interested in learning more about this or talking to me about this, then please chat to me or write to me. Yeah, so this is was this clear? I'll stop here for any questions.
Question for what? Did you like come here?
Hi, can you hear me?
Hello. Yes.
These red dots are JWST observation.
Yes. Yes.
So, and the blue curve is the stellar population. Is that right?
Mm-hmm.
So
Yes.
it seems that all of these red dots are dominated by stellar populations, and the contribution from the torus is minimum. So, how accurate can we trust this?
So I'll that's a very good observation. I'll come to this exact point later
Okay.
as to is this even useful?
Okay.
Um, and as you say, this is mostly dominated by stellar population, and this is sort of a spoiler. That is because this is a heavily extinguished AGN, so you don't see much light in UV. You see some light in infrared, UV optical. Sorry. I'll come to your question later, and if you still don't have your answer, then you can ask me this question again, if that's fine.
Thank you.
Thank you.
I think there is no more question right now.
Okay, perfect. Yeah, so this is the main idea of our work. Now we have done all this stuff, but what is the science here? Why what is the point of doing all this? Oh well, the, there's one slide about the software. So this is the software I'm using. It's called FortisFit. My supervisor had started writing this code back in 2017, I think. Um, but he wrote it just for single source and no simultaneous fitting. Um, so I've been adapting this code for simultaneous fitting and making it useful, scalable for population type of analysis. We have 14 free parameters. We keep our redshift fixed. Uh, and don't worry about what you see here. This is just to show that FortisFit gives you so much information that you probably don't need all this information. Um, the main thing here is that it gives you posterior distribution, and it's a completely flexible code. So you can define your own filters, you can define your own models, you can define your own parameters. You can play with your data in different ways. So it's completely flexible code with full Bayesian SED, well, Bayesian inference type of thing. So all the good stuff that comes with Bayesian inference is in FortiSuite. Right. So coming back to science, these are the four questions I'm asking. If we have all this method of doing SED fitting and stuff, what do we want to do? So first question I'm asking is, can we constrain torus parameters in Seyfert galaxies at cosmic noon? This is the question we started with. Uh, I would hope the answer to this is yes. And spoiler, it is yes. If we can constrain the parameters, how does it compare with what we see in local population? Because at the end of the day, we want to see how the torus have evolved. Well, I say torus, but tori because we are doing population studies. So how the population properties of these tori have evolved from cosmic noon to current time. Um, what difference does JWST make? So this simultaneous SED fitting, what was the point of doing all this stuff? And finally, what do we need in future? And as astronomers always say, the answer to that is more observations. But let's right. So we have the SED fitting method, we have the models, we need our sample. And this is a quick checklist for what do we need. So we want to perform population level analysis. So you would hope to get a large number of AGN to marginalize over all the parameters that we don't care about. So for example, star formation rate, inclination angles. Um, we don't want these things to bias our sample. So ideally, we would want a large sample. So it should come from a large, deep extragalactic survey. I have listed some of these, and you would see why I have listed only two here. Um, Second thing we need is we need to construct the central SEDs, those red points you see in the SED. So how do we get those points? We get those from JWST. So whatever field we choose should have JWST coverage. And these are the four major fields that have JWST coverage right now. But when I started this work, we only had EGS from Sears. So that is what I've been using. My next, well, I say next job, but I'm already doing this now, is to expand this to Cosmos Web. Last thing we need is we also need the integrated SED or the white points in the SEDs, and those come from multi-wavelength surveys in the past. So if you choose a popular field, you would have multi-wavelength surveys. So EGS, for example, Cosmos, all these fields are multi-wavelength surveys. Right. So as I said, I've chosen to work with Sears or EGS field. What observations do we have in Sears? We have 7 near infrared filters from 1.5 to 4.5 micron from NearCam. We have 7 mid infrared filters from 5.5 to 21 micron from MIRI. And we have images in these filters. We don't have all the filters for all the sources, but some combination of these filters. Um, Archival data, well, X-ray data comes from EG6. UV optical comes from Candle's popular survey, and far infrared comes from HELP, which is a Herschel survey. Right. So how do we define the sample? We could have defined sample in different ways, and each of the sample selection techniques have their own biases. Um, it's fine to have biases as long as you understand those biases. So we wanted to maximize the understanding of biases and also the maximize the number of sources we get. And X-ray selection is known to give you most AGN at these redshifts. So we went with X-ray selection. It was straightforward as well. Um, we applied 2 to 10 keV cutoff, 10 to power 42 ergs per second. Some of you might think that's a lenient cut. You might think that we have a lot of, well, not lot of, but a few starburst galaxies, and that is true. And the good thing is that our SED fitting code actually deals with those well. So if there is no AGN, it says there is no AGN here. So that is not, purity is not an issue for us. We restrict our sample to high quality, only those with high quality redshifts. So either spectroscopic redshifts or very good photometric redshifts. So in the background, you see in total we had 143 sources which were observed in JWST. But then if you apply these two criteria, we get these sources, and some of these also have column density measurements from Buchner 2015. Um, right. So if we apply all these, we get 88 sources between redshift of 0.6 to 3.5. Um, and coming back to questions directly, can we constrain torus parameters in Seyfert galaxies? So this gives you Seyfert galaxies. Can you constrain these parameters? Just one quick thing of what we mean by constraint. Um, how do we define a parameter is constrained or not? So for example, this is, if you assume this is some parameter which we gave a uniform prior for, then if your posterior distribution looks like this, you would say, well, it is not constrained, um, because your posterior distribution looks very similar to your prior distribution. This you would say it's constrained. This you would say it's a limit. I don't know what is happening after this point, but it's still a limit. Um, so we count both of these as constrained and this as unconstrained. How do we do this? We don't sit and examine posterior distribution of each of these. We calculate the Kullback-Leibler divergence, or KLD. I refer to that as KLD, between these two parameters. So between these two distributions, and we set a threshold of, if these two distributions are above this threshold, different above this threshold, then we say that it's constrained or unconstrained. Right. So if you have this definition of constrained and unconstrained, what you can do is you can explore, well, the most basic thing you would expect to correlate with constraining power is how powerful your AGN is. And one independent way of measuring how powerful your AGN is using X-ray luminosity. We already have X-ray luminosity. So what we did was we plotted all the parameters as a function of X-ray luminosity. I'll walk you through this big diagram. First, what we see, these are the parameters that we care about the most, AGN parameters. These open points are unconstrained as we defined in previous slide, and these solid points are constraint points. And what jumps out here is that there is this line of X-ray luminosity of greater than 10 to 43, above which you get more field points as compared to what you get below this. So this basically means that you can constrain AGN parameters better above this X-ray luminosity, which makes sense. You have powerful AGN, you can constrain the AGN parameters. But that is the first thing that jumps out to you here. And what we have done is that we have applied this cut for rest of the analysis. So we remove all the sources below this cut, and we do all the analysis about this. So that removes 22 sources. So our sample size, which I said 88 in the beginning, is 66 now. Second thing we see is that we can't constrain some of the parameters. So these you see, all of these are related to how the dust is distributed within the torus. We can't constrain these things even in local AGN. So there was no hope anyway for constraining these parameters at high redshifts. So that is just confirming what we already expected. This is one galaxy parameter which is related to how the dust temperature in the galaxy, and this also we can't constrain in most of the local sources. So it's not surprising that we can't constrain this at higher redshifts. And third thing we notice is that there is no obvious correlation between X-ray luminosity and AGN parameters, except for this, which is the UV luminosity of AGN and X-ray luminosity. And We already know this relationship exists. So it's nice that we see it. It's a good validation, but it's nothing new. Um, right. Second part of the question was, can we constrain these in a robust way? So these are some validations of of whether this SED fits are robust or not. So we see that stellar mass actually peaks near 10 to 11 solar masses, which is typical for galaxies in EGS. Uh, the second thing we notice here is that the time scale for star formation is quite small, and this we interpret it as the stellar population is quite old, um, which is to be expected because these are massive galaxies. So nothing too surprising. But if you have any alternative um, interpretation, then please let me know. These are the parameters of AGN. AGN luminosity peaks at 10 to 44 hour per second or 21 AB Mach, um, which is again expected from X-ray luminosities. Uniform inclination angle, that's good. That means our fitting is not biased or selection is not biased. Um, and finally, 8 to 1000 micron luminosity, as I was alluding to, is related to star formation rate. This translates to roughly about 15 to 50 solar masses per year, which is slightly below what you would expect. But then we don't have that good of a data in far infrared anyway, so we don't expect to have this tied down in a very robust way. Right. So answer to this is yes. Uh, can we, so this is now coming to evolution of how do these parameters compare to local population? So this is the main result, the money plot in my paper, in my work. This is the covering fraction distribution in 66 sources that we have in our sample. What you see here is that there is an excess of low covering fraction AGN, and then it flattens to almost flattens to all other covering fractions. And this we know why this is happening. Ideally, you would say there should be no preference for covering fractions, so this should be flat. And this we know why this is happening is because X-ray selection is known to be biased towards type 1 AGN, which usually have low covering fraction. So not too surprising. This is likely because of the bias. How does this compare with? Oh, by the way, these are still cartoons of what low covering fraction, high covering fraction mean. How does this compare with local sample? This is a similarly selected local sample. What we see is that this peaks and then drops. So do we see signs of evolution? What this is saying is that at high redshift, at cosmic noon, there are more obscured system than what you have at in local universe. Which, if you believe in theory of how the quasars are formed, for example, you have this phase of dust. When dust comes in, you have this phase where quasar is heavily obscured. So if you believe in that theory, you would say that, well, this is the sign of that at cosmic noon, many systems were obscured, and then slowly those systems became unobscured or less obscured. But I'm going to say that this is a false alarm. This is not the case. These two populations are actually consistent with each other. Why am I saying that? Because this green line, this was obtained using an SED fitting method, which doesn't give you posterior distribution. It just gives you the best fit method. Sorry, best fit values of your parameters. So if we come back to this plot, um, we have full posterior distribution. We compare it with prior distribution. And if you take median of these distribution, that is the kind of value you get from that is the kind of value that was used to create this plot. And this doesn't account for any uncertainty. This cannot identify unconstrained sources. And that is why it's not apples to apples comparison. And in order to get a similar comparison, what we do is that we take median value, which is yellow, and then we remove sources which are unconstrained. Because if you had given a different prior, that is the posterior, that is the best fit value the fit would have returned. So it's not fair to use those values in posterior distribution. So if we do this kind of um, analysis, create an equivalent best fit and remove unconstrained sources, then what we get is this. And this is consistent with what we see in local universe. So peak and then it drops. So if you ask me right now, I would say that within the sample that we have, we don't really see any signs of evolution in AGN torus. But I would also caveat it with saying that there is only 47 sources. And if you remember, my sample distribution was from zero point 0.6 to 3.5 redshift. So that's quite a large range in redshift. So probably it was not even suitable to do this kind of study to begin with. Right. There's only two more things that I want to show now. We also there's also theories that type 1 and type 2 AGNs are intrinsically different. So we wanted to test that. So what we have done here is that we have divided these AGNs into type 1 and type 2 based on the AGN model. And what we see is that type 2 AGN generally have high covering fraction, type 1 AGN have generally low covering fraction. But we do get some type 1 AGN with high covering fraction and some type 2 AGN with low covering fraction. This has been observed in local universe, so it, it still stands at high redshift. So that's the only thing we can get from here. But this I find quite interesting. Another way of distinguishing type 1, type 2, I wouldn't say type 1, type 2, but obscured and unobscured sources is using X-ray column density. And if you divide our sample using this, we see that these two populations are actually quite consistent with each other. So what this says is that X-ray obscuration probably comes from a different region than infrared obscuration. Um, I don't know what that means theoretically. Um, that is for simulators and theoreticians to tell me. But I found this quite interesting. Right. So answer to this is, are these populations different? Well, not really. Not so far at least. And finally, this question, what difference does JWST make? And this would answer the question that was asked as well. So these two fits, if you look at these two fits, just look at the white line. You see that both of these fit are quite good fits to the data, right? Um, but if you look at the AGN component, it looks very different between these two fits. And if you look at the posterior distribution, those two also look quite different. So this is saying that this AGN is obscured. This is saying this AGN is not obscured, well, less obscured. This AGN is brighter, this AGN is fainter. So how do you distinguish between these two? Well, this is where JWST comes in. So if you were to plot JWST points here, you would see that this is not consistent with what you see anymore. So best fit model white line is not consistent with your observations. But here your white line is actually consistent with your observations. So what you gained using JWST is that you said your AGN is not bright in UV optical, whereas there was room for AGN to be bright in UV optical when you didn't have JWST. So actually what JWST did was it gave you a more accurate modeling of the AGN. So without JWST, you could have inferred completely different AGN luminosity and completely different covering fraction of this source. There's one more example. So these two, again, these two look quite a good fit. This I would say actually is a bad fit, but because the data is bad, we treat these as limits, so it's not a bad fit. Again, posterior distributions are different. If you put in JWST data, one of these is completely wrong, and one of these is consistent with what you see. So this is the value of JWST. These are some specific cases which I obviously cherry picked. How does this look on population level? Well, we see, so this is if you are using only integrated, and this is doing the simultaneous fit. Uh, Opening angle or vice versa, covering fraction distribution is quite varied. So some of the sources with low covering fraction actually become high covering fraction. Some with high covering fraction become low covering fraction. But what is more important is that we get systematically lower constraints. So these are 1 sigma limits on the posterior distributions. And we get systematically lower errors on our AGN parameters. So that's good. That is something that, so we can trust these more. And finally, we see no obvious correlations between like coverage. If you have only MIRI versus, so if you have only near cam versus if you have both, we don't see any obvious correlations between these things. Yeah. So what does JWST do? It gives you tighter constraints and also improves AGN modeling. What am I planning to do in future? I'll leave this slide in the end. Just to give a quick summary. So this is the first study which constrains the covering fraction in population of Seyfert galaxy, which can be compared directly with what we see in analogous populations in local universe. We have used simultaneous SED fitting, which actually fits large scale and small scale SEDs at the same time self-consistently, and that gives you better, tighter constraints, precise AGN modeling, and all that good stuff. Science-wise, we find that there is still no sign of evolution within this sample and within these uh, these models of AGN. Um, and a word of caution is that how you do the SED fitting can actually change how you interpret your results. So if we were not careful about the best fit kind of value versus what we were doing, then we would have reported this as well. This there were more obscured AGN at cosmic dawn. So this is a word of caution. Um, and finally, this is some future work, but I'll leave this slide up and I'll um, take any questions.
Thank you, Devang.
Thank you.
So, questions?
Did I answer that question? Can I ask first?
Have you?
Hi, can you show the fitting results again?
Yes.
With and and without the so with JWST you use a different stellar population for that to constrain.
No, so this is the same stellar population that is scaled down.
Oh,
now.
scale down. Oh, okay, okay. I see.
Yes, yes, yes. But this is something I've heard that you have lots of galaxy people there. So this is something I would like to improve on. Maybe we can fit two different stellar populations. Or if
Yeah.
there is a better way of getting this scaling constant, because right now I'm doing some hand wavy way of identifying what is the scaling constant. But if there is if there is a better way of doing that, then I would love to know that. But yeah, this is the same stellar population that is scaled down.
Okay, I have no question. Thank you.
Okay. Did I answer your initial question though?
Yes. We have a question from Garrett.
Yes.
Yes. Yeah, good talk. Thank you. Can you go to the slide with the PDF of the covering fractions?
Was it these ones?
No,
Oh no, the
it's
covering
further
fraction.
back.
Right. Yes. Do you want this one or the
Yeah.
other one?
So, obviously these are broadly consistent, as you said. Obviously, the high Z, yes, the high Z has a lot less sampling. So I guess I'm looking at kind of the dip in the middle, which may just be a statistical fluctuation. What are the odds of seeing that kind of dip given the sampling you have? Or have you run that?
I have not actually done the test on that, but I
Yeah.
should. Yeah, that's a good question. Yeah.
Yeah, it's one of those esoteric. I could look at this, but
Yes.
don't really does it really. Yeah. I agree with you that they're broadly consistent. I'm just kind of curious like how rare this kind of dip would be, given the
Yes.
sampling you
That would
have.
be that would be a useful thing to measure. Yeah. Did you have any specific follow-up to that? As in, did you have any reason to see the dip or not
No,
see the dip?
not particularly any
Right.
reason.
Okay.
My
Okay.
next follow up, like, well, yeah, I'm just curious, I guess.
Mhm.
My instinctual follow up is always like, well, why would there be a dip? But we haven't rolled
Yes.
out the
Yes.
statistics yet, so it's not really a useful question. Yeah,
No, it's a useful question in the sense that I should do this.
yeah.
Yes. Yes. Thank you.
Mm-hmm.
Hi, great talk.
Hello.
I had a question. This might be outside the scope of the research, but one of the things JWST has been finding are these little red dots, which I'm sure you're aware of. Um, I'm just curious, do you think that there's any hope of doing this type of modeling for those sources? And have you thought about that or have any insights or those are much higher redshifts. So I'm just curious what your thoughts are.
I've actually recently talked to someone about doing this kind of stuff for little red dots.
Okay.
But the problem is that little red dots, you can't play this game of central SED and the integrated SED because those are little and they would be completely probably encircled um, inside the aperture. But what we were thinking was this JWST points cover a new range in the SEDs, right? So even with integrated SEDs, can we do something about that? I don't have any expectations of what that might look like, but it's an interesting thing, and I'm thinking of doing something like that.
Cool. Thank you.
Thank you. It would even be useful if we can classify that little red dots, for example, are definitely AGN or definitely obscured AGN or something like that. Even something as simple as that would be quite useful, quite interesting as well.
Okay. Thank you, Devang, for joining us today. Thanks. That was a
Thank
great
you.
talk. Thank you.
I'll just flash my team members here. Please come visit us. Please talk to us.
Yeah.
Thank you.
Thank you. Have a good day.
Bye, you too.
Bye.